Hey, welcome back. In our last video, we talked about how to find a limit using a graph or a table. Today, topic 2, we're going to talk about how to find a limit algebraically. The way you do that is with what we call direct substitution, which means if you have a limit, take the value of x that you're approaching, plug it in, and if you get a value, great, the limit exists, that's your answer. If you don't, if you get 0 over 0 or something weird like that, you might have to do a little bit more work. Okay, if you look at the top here, you see I've got some limit properties. Take a look at those. I don't want to go over them too much because really it's common sense. This works the way you probably think it should work. So what I want to do is instead get some practice with direct substitution right away. So example 1, the limit as x approaches 3 of 2x plus 4. Direct substitution means take this 3, plug it in everywhere you see an x. So I get 2 times 3 plus 4. 6 plus 4 is 10. It's that easy. Okay? No graph required, no table required. Direct substitution is always going to be the first thing you try when you see a limit from now until forever, including right now. Example 2. Find the limit as x approaches -1 of 2x plus 1 over 5x squared. So we're going to take this -1 and we're going to plug it in for x there and there, giving me -2 plus 1 over 5 times -1 squared. -2 plus 1 is -1 over 5. So the limit as x approaches -1 of this function is -1/5. Example 3, find the limit as x approaches pi over 6 of cosine x. Well, direct substitution pretty straightforward here. I'm going to have cosine of pi over 6, which, if you think back to your unit circle, cosine of pi over 6 is the square root of 3 over 2. That's it. Direct substitution works great when it works. And the reason why I say that is because, look at example 4, the limit as x approaches 3 of x squared minus x minus 6 over x squared minus 2x minus 3. If I try direct substitution here and I plug in 3, I would get 9 minus 3 minus 6 over 9 minus 6 minus 3, which equals 0 over 0, which we call an indeterminate form. Okay? Some people might be tempted to say 0 over 0 is 1, but that's not necessarily true. We've got conflicting rules here because I know that 0 divided by anything is 0, but I know that I'm never allowed to divide by 0. So when you stick these two things together, it's what we call indeterminate. So our strategy for indeterminate forms is try to factor or possibly multiply by a conjugate. So when I look at this problem again, knowing that direct substitution yields an indeterminate form, I'm going to ask myself, does this factor? So x squared minus x minus 6, that's going to factor into x minus 3x plus 2 over x squared minus 2x minus 3 is going to factor into x minus 3 x plus 1, and sure enough, when I factor this, what I see is that these x minus 3 terms cancel out. If you think back to pre-cal or algebra 2, this is a rational function with canceling factors. So what that means is that this graph has a hole in it at 3, which is why I couldn't plug in 3. So after canceling, what am I left with here? I've got the limit as x approaches 3 of x plus 2 over x plus 1. And now direct substitution works just fine. Take a 3, plug it in, 5/4. So what that means, just thinking about the graph has a hole at the point 3, 5/4. But the value of the limit is 5/4. Okay. Next up, we're going to have the same problem here. When I try direct substitution, plugging -2 into 2x squared plus 7x plus 6, that's going to give me 2 times 4 minus 14 plus 6. 0 on top, over 3 times 4 minus 10 minus 2, gives me 0 on the bottom. Something to be careful about, real quick. On your work, like on an AP exam or even a test you take in class, you don't want to write equals 0 over 0. Okay, because technically it's wrong if you say it equals 0 over 0. Look at this example up here. If you said this equaled 0 over 0, that would be incorrect. It doesn't equal 0 over 0. It equals 5/4. So be careful about that. Generally what I do, if I have equals 0 over 0 written on my paper, is either cross it out or erase it. Okay, because that's part of the work that tells me to factor, but it's not part of the answer, and I don't want it to be confused with the answer. So here, let's say I'm working example 5, I'd probably get to this point, and then I would destroy the evidence, right? There was never a 0 over 0 here, and I'm going to try and factor this. When it comes to factoring problems like this, there's 100 different ways to factor. Teachers all over the country teach it lots of different ways. I would say find a way that works for you. Okay, some people prefer guess and check. If that's your style, great. But I'm going to assume for our purposes that you know how to factor. So the numerator, 2x squared plus 7x plus 6, is going to factor down to 2x plus 3 times x plus 2. And the denominator is going to factor into 3x minus 1 times x plus 2. And what do I see here? I've got terms that cancel. So this limit is equal to, the limit as x approaches -2, of 2x plus 3 divided by 3x minus 1. Try direct substitution now. I've got -4 plus 3 over -6 minus 1. It's going to be -1 over -7. It's 1/7. Example 6, the limit as x approaches 16 of the square root of x minus 4 divided by x minus 16. When I try direct substitution, the square root of 16 is 4, so I have 0 on top over 0 on bottom. Indeterminate form tells me either factor or multiply by a conjugate. Okay, this is going to be a multiply by a conjugate problem. Okay, what is a conjugate? Take the term with a radical in it, take the operation in the middle, and change it. So I'm going to multiply by the square root of x plus 4 on top and on bottom. So I'm multiplying by 1, but when I do this, it's going to change the way this looks. This problem is going to become the limit as x approaches 16 of, we're going to FOIL this, so square root of x times square root of x is x, plus 4 square root of x minus 4 square root of x cancels out, minus 16 over x minus 16 times the square root of x plus 4. And here we see again, these terms cancel. So this limit is equal to the limit as x approaches 16 of 1 over the square root of x plus 4. And now direct substitution will work for me. 1 over 4 plus 4 is 1/8. Next example, another conjugate one. Feel free to try it on your own if you want to. When I plug in 0, you can pretty quickly see you're going to get an indeterminate form, 0 over 0. So I'm going to multiply by the square root of x plus 4 plus 2 in the numerator and the denominator, giving me x times the square root of x plus 4 plus 2 over x plus 4 minus 4. Well, x plus 4 minus 4 is just x, and these x's cancel out. So this limit is equal to the limit as x approaches 0 of the square root of x plus 4 plus 2. Plugging in 0 gives me the square root of 4, which is 2, plus 2 is 4. So if you try direct substitution and you get an indeterminate form, try factoring or multiplying by a conjugate. We're going to shift gears a little bit. Before we move on, we've got some special trig limits, and I can't explain to you why these work yet. Once you know a little bit more calculus, we can come back and revisit these, but for now, take my word for it. The limit as x approaches 0 of sine x over x is 1, and if I flip the numerator and the denominator, x over sine x is also 1. The limit as x approaches 0 of 1 minus cosine x over x is 0, and if I take the terms in the numerator, make them switch places, it is still 0. The limit as x approaches 0 of cosine x minus 1 over x is 0. So using these, we'll try and answer these questions right here. The limit as x approaches 0 of tangent x over x. Well, if I plug in 0, I'm going to get 0 over 0, so we don't want to do that. But I can rewrite this as tangent x would be sine x over cosine x over x So I can write this as the limit as x approaches 0 of 1 over cosine x times sine x over x. And I know from my trig rule up above, the limit as x approaches 0 of sine x over x is 1. And when I try direct substitution, plugging in a 0 right there, cosine of 0 is 1. So I have 1 times 1 is 1. Example 9, the limit as x approaches 0 of sine 5x over x. Okay? I want to point out the rule up above, I can sort of extend that. If this problem was sine 5x over 5x, it would be 1. Okay? It's not. It wasn't written that way. I can't just put a 5 there because it's convenient for me, but what I can do is multiply the numerator and the denominator by 5. So what I've got now is the limit as x approaches 0 of 5 times sine 5x over 5x. Okay? And using my new rule, this limit is 1. 5 times 1 is 5. Example 10, same property as before. Okay? If this 4 was instead a 3, everything would be great, but it's not. So to make this work, I'm going to multiply by 3 on the top and the bottom. So my new problem looks like this. The limit as x approaches 0 of 4 over 3 times 3 over sine 3x. And now I recognize this as the limit. In the limit as x approaches 0, this is going to equal 1. 4/3 times 1 is 4/3. Okay. And lastly, from the 2008 exam, number 2, the limit as x approaches 0 of 2x to the 6th plus 6x cubed over 4x to the 5th plus 3x cubed is what? Well, if I plug in 0, I'm going to get 0 over 0, but I can see that this factors. I can factor out a 2x cubed on top, leaving me with x cubed plus 3, over, I can factor out x cubed on bottom, leaving me with 4x squared plus 3. Okay, the x cubed and the x cubed will cancel. And when I plug in 0 now, I get 2 times 3 over 3. 6 over 3 is 2. So to recap, when we're evaluating limits, the first thing we're going to try is direct substitution, meaning plug it in. If you get an indeterminate form, 0 over 0, try factoring or multiplying by a conjugate to see if you can simplify your answer. Also, we have new trig limits that we need to memorize. Okay? Hope that helps. Thanks for watching.